So let's cover a quick agenda. So we've already done the welcome. I'm going to shortly introduce our presenters. We're going to cover a few things regarding the SDK, an overview of how to use the CLI. That's the command line interface. We're also going to cover using the Python APIs built into the SDK with our presenter, Tom. And then we'll go over a quick summary and then live Q&A as we discussed. So our presenters today are going to be Michael Turner, a field application engineer in the Americas. He's going to be covering the command line interface. And then Tom Slankard, a staff software engineer, who will cover the Python APIs. Before we move forward, I wanted to say, Ouster, we're making continuous innovations in the tools we provide to make lidar data more accessible. We want to help you configure, visualize, analyze, manage, and share data more effectively. The SDK is an important part of the toolkit, but we have launched other tools such as the community forum, Ouster Studio, to make the vision a reality. Today, we'll highlight the Ouster SDK. There's too much to cover comprehensively in just 1 hour, so we're going to focus on introducing the SDK, how you can configure, visualize, save, and record data. Right now, I'd like to hand it off to Michael Turner from my team. So Michael Turner, please take it away.
Awesome. Thank you. Welcome, everyone. I'm glad to be here. Yeah, as Christoph mentioned, I'm Michael Turner. I'm a field application engineer. I've been with Ouster for over 3.5 years now. It's a very exciting company with lots of exciting things to share and showcase. So yeah, I'm based out of Ohio as well. So that means, yeah, let's just not talk about college football for a while. Thank you. So yeah, let me begin with sharing my screen and we can get started. Effectively, what do I want to cover today? Let's see, I don't see my screen. Give me just 1 second. Okay. Yeah, so what I really want to cover today is the Ouster CLI. I'm going to take about 15 minutes or so. And I want to show you how you can use it as the previous slide was suggesting, where we can discover, we can configure, we can visualize, save, and record. So starting with the overview here, we look into the docs. The docs are a great resource to guide you through all these various steps that I'm going to essentially do today. So if you ever feel in doubt or just don't know, it's in the documentation. Specifically, tends to be under the command line utility, getting started, full command list. So what is CLI anyway? What is the Ouster CLI? Well, it's much more glamorous, I guess, than the docs here would describe. For me, the basic definition I can give you is it's just a simple, straightforward command line utility to help speed up, streamline all the common sensor tasks that you have and data recording tasks with the sensor, and using other data that's previously recorded from other sensors as well. And the CLI is included in the SDK. So I guess the question, why use it? Well, what I want to demonstrate today is basically the reason why I use it nearly every day that I work. Obviously, I work for Ouster, so I have a need to work with lidar data a lot, but I think it has a lot of utility for everybody. So it kind of gives you like the most comprehensive set of tools and functions for working with Ouster sensors, and there's zero coding skills, which is always nice, especially for me. I'm I'm an active Python user, but I wouldn't consider myself an expert, and nobody's paying me for my Python skills. So you just open the terminal, use the command line, and that's it. And I think the last little thing I'll say is, once you start using the CLI, you get more understanding with running commands and scripts from a command line. So it takes that fear out of that, and it's built directly inside from the Ouster SDK. So everything that the CLI provides was built from the SDK, and it gets you a lot closer to just start working with Python, which I think is great. Okay. So the first thing is actually common use cases. The first thing is an installation of the CLI. Again, it's included with the SDK. I won't cover that here. we actually have a few existing examples to walk through for anyone step by step. It's actually really super easy to do. You just need Python and a terminal. Then you pip install the SDK, the Ouster SDK. So we can provide links, or it's in the SDK docs, as well as a couple of videos on YouTube channel covering the installation and initial setup. So the first the first thing we want to do on our CLI journey is called discover. Oh, I also wanted to mention I have you can't see it here in my video, but I have a live Ouster sensor sitting next to me on a tripod. Um, so when I show it live and work with it, it's just right next to me in my office slash bedroom. Okay, let's do this. So Ouster CLI, we're going to do what's called discover. Ouster CLI, we type this in here, discover, no typos. Aha. So this information that I'm getting from the sensor now with this Ouster CLI Discover is very useful because I'm reaching out on the local network and finding the details about my sensor that is present, including, its host name, its IP addresses, all the information you need to start beginning communication with it. There's other ways to, you know, parse out or determine what the host name is for the upcoming steps. One of them is on the product label. There's a serial number, so this is where that host name comes from. It's OS dash the serial number. It's printed on the top cap, but we don't need to read. We need to read a small print. We just send a command, and now we have it. So now that we know our sensor, I'm going to copy this, and I am going to visualize the live LiDAR stream. Ouster if I could type, CLI. We're introducing a subcommand called source. Source basically is saying, what is your source that you want me to visualize or further process? And that could be a live sensor, or that could be pre-recorded data. So in our case, it is OS, copy, paste, and then viz. And then it'll immediately, screen will pop up. And now we're rocking and rolling here. We've got a live point cloud, super cool. This is my little office room, bedroom. You can see me waving here. So we're working with the point cloud. Once in here, there's a ton of ways to um, modify some of the viewing settings, change just how the point cloud is colored. Right now, I'm coloring it based on a field called reflectivity. It's like echo strength. It's an indication of echo strength. So I got all the range points in the cloud, and I can kind of cycle through some of those based on signal, based on the near infrared, based on range, and then coming back. Increase the point size, zoom in, zoom out, just like you would in any CAD program. Pretty cool. This is fun. What do we do with this? And what's next? So next we'll show a configuration step. But I did want to just mention here, these 2D images they look very curious here. Now, Tom Slaker, my colleague, he'll detail this out a little bit more coming up, but Ouster lidars are kind of unique among spinning lidars in that they're designed to output very structured, organized point clouds. So similar concept to the 2D range images that you may output from devices like a Kinect, a RealSense, or even a traditional kind of camera. The pixel counts of course very different, but structured data is similar. Okay, the last little thing to know, before I go to configuration, check out that we're visualizing the point cloud with the default settings. So I've got a full 360-degree field of view. And also I wanted to show that by default, there's a 50 centimeter minimum working distance, basically an area before the actual measurements start happening. It's there by default to maintain backwards compatibility. But okay, we can see if you look in the 2D images, it's a little bit more apparent that there are no measurement values. It's just black. So I'm going to change that in my next step here. Let me just check, make sure. Okay, configuration. Oh, by the way, just press the escape key. It's pretty straightforward and intuitive to do so. Okay, it's bringing it up on the wrong screen. See, this is what happens when you sometimes do things live. They end up on different screens and okay, so on to configuration. Let's talk about just configuration in general. You know, there's a lot of use cases, real life use cases that Ouster supports and Ouster sensors are currently installed. Very, very broad from different industries like robotics, industrial, self-driving automotive, and others, including mapping. So Ouster configuration by default covers most of those needs, at least in the early prototyping stages, but there are other knobs to turn to kind of dial in the use case and the need here. So things like increasing the, I just bring this up. I think this is interesting. This is the full list here. We've got all these little knobs to turn effectively. And the knobs that I'm going to turn today is I'm going to save a little bit of data in an area that I'm not using by configuring an azimuth mask, or basically silencing a portion of the horizontal field of view to effectively 180 degrees. And I'm going to bring that measurement down to 0 centimeters, right to the window, because that was newly introduced in firmware 3.1 for Rev 7 sensors, which is really cool. Okay, first, Ouster CLI config. And I'm gonna print this in my terminal to see what's going on now. Um, oh, I forgot the host name. Let's see, source, put the host name here. Nope, it's not. Okay. Okay, and I'm going to config and print it. There we go. So this is the default set. You can see my settings here, including like the azimuth window. Um, yeah, all the parameters, so you can just take a quick view at those. But what I'm going to do is I am going to config. I'm going to change this to a min range threshold in centimeters of 0, as well as, and I'm just going to copy and paste it over here to specifying the azimuth window. I'm doing it in milli-degrees. That's how the input parameter is inputted for this configuration. So 90,000 or 90 degrees to 270. That's effectively the front half, front 180 degrees. Do this. Okay. I get that it's updating. Give it about 5-10 seconds here to store those settings and be operational for measurement. I guess I can check them here. Mr. Clay, print it, and you can see what's changed. But let's look at what's changed. Let's just visualize. All right. So we can see immediately half the room is gone. Yeah, so that's effectively showing that you can configure. There's other ways to configure the device as well. You know, you can do it from the web UI, the built-in web server. You do it from our standalone desktop app called we call it Ouster Studio Desktop. Sorry, and those are other means to do this. But doing it inside the CLI environment, I think, is important because you want to have your whole workflow kind of embedded in this terminal or something, and that's why I like this the addition of the config. And also, let's zoom in here. And now you should be able to see, yeah, there it is. Remember it was black before, and at least in the reflectivity. So what I'm showing a range here, but yeah, I can measure all the way to the window now. All right. I am just going to set that back, close this, clear this. And I'm going to just set this back to, I'll keep it at 0 centimeters, but the original full 360. Okay, so that was fun. That was config. Again, we have this kind of metered out here in the documentation to follow along. Yeah, configuring the sensor. The next thing that I am going to do is called save. Now, save and record kind of mean the same thing as far as the Ouster CLI is concerned. It's the ability to take a live sensor or multiple live sensors. It's the same time and save that data into some kind of file format. Um, or it's a way to kind of bring in an existing pre-recorded file, modify it, manipulate it, and save it as another type of file. And what's cool about the latest, I'm sorry, latest firmware update and SDK updates really takes advantage of things like PCAPs, ROS bags, OSFs, which is an Ouster sensor format, open sensor format, LAS, PLY file types, and PLD. Those are all possibilities for manipulating and saving data. So what I'm going to do here is just the very basic of the basic. I am going to visualize the sensor, but I'm also going to introduce save. And I'm going to save this, maybe 5-10 seconds worth of this live sensor in something called capture1.pcap. PCAP is a pretty familiar, Wireshark and lidars use as well, pretty standard format. So it's working, and I can bring this over to visualize. I'll wave my hand, and pressing escape closes the viz window and it stops the recording. And now we can see that, hey, there's a capture1.pcap, and there's a tag along JSON file, which is the associated metadata. So we can visualize that. I guess I can bring that up really quickly. But let's just do the same thing. Instead of focusing on the PCAP, let's do the same thing, but let's save it as an OSF. There's the OSF, the open sensor formats, fairly new in terms of how are adding this to the SDK tooling. But there's some really nice advantage of OSF, which Tom will hopefully touch on a little bit of the basic concept, right, and using it. But file size is much more reduced compared to a PCAP, and you can also write custom data fields into the OSF when you're saving it. So it could be um, it could be a lot of things. It could be IMU data. It could be just a data stream of some kind. So as you capture additional fields, so that you can replay that back and work with it. Okay, saving the capture. I'm not going to show let me show the viz. Okay. Again, same kind of idea. With my hand, I want to get maybe 100 frames or so. Closing, and it should be there. Indeed. We can visualize that. Yep, forgot the source. Remember, your source now is the pre-recorded file. It's no longer the sensor. Okay, give me just 1 second. This was all planned, by the way. There we go. And there it is. But what I want to do is introduce something additional to process pre-recorded data. It's called the slice command. Slice is a command that it allows recording like a fixed time duration or a fixed amount of frames of the lidar. So you can you have two indices, the start and the stop, and maybe perhaps I'll give an example of that. So I want to slice, and the indices here I'm going to use our frames. I'm just going to take frame 0 to frame 2 and save those as capture, what we want to call it, whatever, capture 2. And I'm going to save it as a CSV. And there we go. I can print this. Okay. And print it out by frame. It's a lot of data there. You could open this in Excel. I'm not going to here. But for those familiar with CSVs, CSV files, that's cool. We can also do the same thing. Instead of a CSV, how about we do a PLY? What's interesting, so we have the PLY. What's interesting about the PLY is I can then further process it in point cloud, open source point cloud tools that are more familiar and have a lot of utility that from manipulating these file types. So I'm going to open this. Let's just see. I can actually, there's a scaler. We can paint it by reflectivity. That's carried, yes, apply. And there we go. It's a frame. And for those kind of uh, familiar and the nuances of cloud compare, I think this is a good exercise to showcase. Okay, so let me remove that. I think I'm getting pretty close to my time allotment, but before I give it to Tom, I just really want to go through a quick demo of Ouster CLI Slam. Um, it's super cool. We can use it here because we just covered all these kind of techniques in the CLI today, kind of in the effect to hit the go button and just jump right in. So let me do that here. Cool. So Ouster CLI Slam, for a little background, um, Slam is it's a technique to create a map of the surroundings and simultaneously determining its position within that map. It's not, and funny thing is Slam is used so interchangeably these days. It's meaning it's not really one specific software app or set of algorithms. It's a much more broad term that kind of can describe many techniques to effectively just allow autonomous vehicles to move autonomously and while referencing the map that's created, or just for general mapping use cases. We use it to determine the sensor's movement trajectory and reconstruct a really detailed point cloud. So what I'm going to do with the time array, I'm just going to build a really nice map from a pre-recorded data set. I'm going to run SLAM on it, and yeah, always following along. There's some really good tips and kind of a really good walkthrough on how to do this yourself with SLAM with a pre-recorded data set that you can grab, and there's sample data as well from Ouster's website. So I have a pre-recorded file, Ouster CLI, introduced to SLAM. Actually, I forgot the source again. Where is it coming from? So it's a PCAP that I have in my directory, and I'm gonna SLAM and viz. That's the most kind of basic. What was that? Ouster CLI source. Yep, that happens. Okay, much better. Sorry about that. There we go. So notice in here what we're seeing now is all the poses, all the captured poses are plotted out for this trajectory here. I'm not really showing much else. Let me get rid of this. But yeah, this is representing the path that the vehicle took while recording simultaneously. Um, Pretty neat. And there's a lot of commands that I won't show today, but a lot of tunings that you can do around the SLAM algorithm in terms of like voxel size. I will show min range, but there's also a maximum range toggle. We can change the color scheme here. There, we're changing the points. And it is done. Okay, it's just kind of slow. It's laggy a little bit. So we can change it based on signal. We can change the color palette, which is fun. It's not changing. There. All right. Many different options. Cool visualization. But let's do something a little bit more dangerous here. Let's add a minimum range into the SLAM by introducing the clip feature. So the source is still the same. What we're going to do is we're going to clip minimum range to 3 meters. And if you notice when I had it streaming live here, you see a lot of points that are intersecting the vehicle. Let's say I don't want those to contribute to the map, so I'll introduce this clip feature to clip the minimum range and pass this to the viz. And let's see. Now we can see, yeah, a lot less contribution here from the vehicle. Yeah, it's pretty simple, straightforward. The last thing, the fun thing, let's build a map and we'll visualize it with a little bit more visualization. So it follows this here, this overall in our documentation. So I'll just paste this from my cheat sheet. So what we're going to do, um, we're computing poses for each scan and creating the map with the visualizer. We're not altering the original PCAP. We're just clipping them in range. We're accumulating 50 frames every 5 meters, and we're passing this and building a map, this dash dash map. Let me do this, and yeah, try to. So I'm going to remove the point cloud. and the accumulated scans, there's toggles. See the trajectory. We see the what's adding to the map. I'm not creating the file. I'm just visualizing it. So you can always add additional steps to save this as a PLY file, for example. Just my recommendation is don't do them together. Don't do a viz and a save to a PLY at the same time. The slam viz, it's just, it can be a little process intensive. If you have a nice new Mac M1 or M4, whatever the newest one is, maybe not so much, maybe not so bad. Okay, and at the end, it's just going to pause to show the final visualization of the map. There's the points. Here's the original, the last frame. And that is, I'm way past time. Apologies, Tom, coming after me, but thanks everyone for tuning in and paying attention.
Right on. Well, thanks, Mike. And thanks to all of you for being here today. I'm Tom Slankard. I'm a developer with the SDK team. And I'm going to talk a little bit about the Python SDK, which is something that's included in this Ouster SDK package that Mike just demoed. And in fact, it's what we actually use to implement all those cool features that Mike just demoed for us. So you can accomplish with the Python SDK, you can accomplish everything that he showed you and more by writing your own Python scripts. So let's get started. Let me just share my screen here. Oh, I am sharing. Okay. Oh, maybe I'm not sharing. Let me share my screen here. Share my screen. There we go.
Yep, looks like it's coming up.
Okay. Excellent. Thank you, Krishna. Okay, so here's what I'm going to talk about. I'm going to talk about how to open a source of Ouster lidar data using the open source method. Similar to the source command in the CLI, this is something that applies to any type of file format that we support in the SDK, PCAP, ROS bags, OSF, and it also applies to sensors. So you can open a source of lidar data using just one method, and it's really easy. It returns an iterable of lidar scan data. You basically get this kind of collection of objects that you can iterate over, and that's the lidar scan data type. And I'm going to talk a little bit about what that data type, how it's structured and how to use it. Essentially, it's just a collection of images, and those images are just NumPy arrays. I'm going to cover how to transform these images, which are in 2 dimensions, into 3 dimensions, so you can actually get point data. I'm going to show a little bit what you can do with point viz, which is a class that we use to implement the visualizer that you're seeing that you saw from Mike. And how you can use the features from the point viz API to create your own visualizer. It's quite extensible, so you can really accomplish a lot with it. I'm also going to talk about adding custom fields to lidar scan and saving any data that you've kind of created through any sort of image analysis or processing or perception that you may have done to an OSF file, and then how you can visualize that. And I'm going to cover kind of more real world example that really showcases the power of that feature and what you can do with it. So let's get started. Copy break. All right. For the first example, this is really how easy it is to open a source of Ouster lidar data using the open source command. Essentially, I'm importing just one method, and then I'm invoking that method with a file path in this case. And then I'm going to iterate over all of the objects in the resulting object that I'm getting from open source, and I'm going to print them out. Each of these objects that we get, like I mentioned, is a lidar scan, which is basically a complete frame of lidar data. So let's take a look at what this does. I'm going to go to the terminal, And I'm going to run this example. And what is all this stuff? So basically, this is kind of the default output from kind of our two-string method for this lidar scan data type. It shows some interesting info about that, about each frame that's in that file that is referred to in script, including the resolution of the images within the scan and which images are present. So you'll see things like range, reflectivity, near infrared, so on and so forth. If you're working with a dual return data set, as we are here, you'll see more than one reflectivity channel, more than one range channel, so on and so forth. So what's in these images, and how can you kind of access them, visualize them, use them, analyze them? Let's take a look. I'm going to go back to my editor. I'm also going to talk a little bit about how these images are represented, or how they're obtained from the sensor, and then how they're kind of represented in lidar scan. Importantly, there's an interesting aspect of these images is that every column in the images as they come off the sensor are time synchronized. And the interesting thing about that is, since the beam pattern of the sensors is somewhat has an offset from row to row, from beam to beam, the images, when you first look at them, appear staggered. You don't really see any sort of spatial correspondence from row to row. So what I'm going to do here in this example is I'm going to obtain one of the images from this data file, and then I'm going to de-stagger the rows so that you can actually see what you're looking at. At that point, the individual columns in the image will no longer have temporal coherence or locality, but they'll be you'll be able to see what's in the images. And so what I'm going to do is I'm going to use that same open source method, and I'm going to use the built-in Python methods iter and next, since this is an iterable object, to obtain the first lidar scan in that collection. And then I'm going to use the field method to obtain the range image from that first scan. And then I really have de-staggering these images is actually quite easy. There's a method that's just called de-stagger that really just requires the metadata associated with the sensor, which contains information about the beam pattern. And then from there, we get a de-staggered field. Then what I'm going to do is I'm going to show these images side by side using Matplotlib, which is a package I'm sure that many of you are familiar with already if you're a regular Python user, especially if you do any sort of scientific computing. So let's see what this looks like. I'm going to go back to the terminal, and we're going to run that example. See here, side by side, the original image as it comes off of the sensor, where every column in this image, it has the same timestamp, and then the de-staggered form. And so in this original image, obviously you can't really see much. Everything looks a little bit fuzzy. But once it's been de-staggered, you can actually kind of see the outlines of shapes and things. You can see these cars here, some trees, some buildings. And so it's really quite easy to kind of visualize these images with really just a couple of methods. It's quite straightforward. I applied a kind of a colorful color palette to these as well to make them look a little pretty. All right, let's go back to the terminal. And let's go back to the editor. So doing basic analysis on these fields is actually really, or these images is actually really easy, because they're all just represented by NumPy arrays when you're accessing them through the Python SDK. And so just to give, maybe a really simple example, there's a lot more that you can do with this, since so many different Python packages support working with NumPy arrays. The possibilities are pretty much endless. But just to give a simple example, what I'm going to do here in this next example, I'm going to do that same thing that I did before. I'm going to use the open source method to get an iterable of the frames in this source file. I'm going to obtain the first scan right here. And then I'm going to read from that scan. I'm going to read the range and near infrared fields. I'm going to go ahead and destagger them so that we can kind of more easily visually see what we're looking at. And then using Matplotlib once again, I'm going to plot those images side by side. And for fun, I'm also going to use some NumPy methods to do some basic analysis. And I'm going to do some really, really basic analysis. Really, all I'm doing is I'm computing the percentile range of these images, and we're going to plot those as histograms. So it's really straightforward kind of analysis. It's perhaps some of the most basic analysis on images you could do, but it kind of gives you an idea, a taste of what you can do with relatively little code. So let's see what that looks like. Just kind of run that example. All right. And so what we can see here in this example is we have our range image plotted with this nice color palette. We see its corresponding histogram here on the right. And then we see the near infrared image, which almost looks like a black and white camera image. I mean, effectively, that's what it is. It's an infrared image, and then the corresponding histogram for that. So just some really basic analysis. And it's just because these are all NumPy arrays. So it's just anything you can do with a NumPy array, you can do with these images. It's really that easy. All right. Let's go to the next thing. Okay. So I'm going to go back to my editor. But ultimately, this is lidar data. And since it's lidar data, you get range data. And since you have range data, you're really talking about 3D space, and you really want, you may really want to visualize this information, this data that you're getting from these sensors in 3D, kind of, in the same way that Mike showed us using the CLI. Programmatically, that's also really easy. One of the things that we've done is we've provided an XYZ lookup table function that, given the sensor configuration, the sensor metadata that has the beam pattern and everything like that, it can produce a lookup table for you that acts as a function, and all you have to do is provide the range image and get a list of points, and it's really quite simple. So just as before, what I'm doing here in this example, I am opening up that source. I'm grabbing the first scan. I'm getting a range image and a near IR image. I'm destaggering those images. And then I'm using the non-destaggered image in the lookup table, because the lookup table kind of handles all of that internally. And from there, I'm getting a list of 3D points. So what I'm going to do is I'm actually going to set a breakpoint here, which will bring up the Python debugger when we run this. And we'll be able to look at what actually has gone on, how that data has actually been transformed as a result of going through the lookup. Then on top of that, I'm going to create a point viz instance that shows this data in 3D. Now, point viz is the kind of lower level API for implementing our visualizers. So anything you saw in the CLI, you can actually do using point viz. In fact, you can display not just point clouds, but you can display two-dimensional images. You can add text. You can even do some event handling. You can handle key events, mouse events, things like that. So what I'm going to do is I'm going to create a point cloud object right here. And actually, the other cool thing about these point cloud objects is that you can provide the range data without having to even transform the points. So that's actually what I'm going to do here. There's a different reason why I've used the lookup table here. I'll explain in a second. But I'm going to pass in the range data into that point cloud. object, and I'm going to add that to our visualizer. I'm also going to give those points some color. I'm going to colorize them using the near infrared channel as the function to map the points to the color palette. And then on top of that, I'm going to add a few other things. I'm going to add a mouse position handler to track where the mouse position is. And I'll show you what that looks like in a second. And then I'm going to add the near infrared image at the top of the screen. And I'm going to add a label and a box, really just a cuboid. And what I'm going to do is I'm going to configure the mouse position handler so that when I have the cursor over the two-dimensional image, that near IR image, it's going to highlight the corresponding 3D point in the point cloud. So I know this is a lot of code. I mean, it's really not that much code, but I know I'm kind of going through this code quickly, but with a comparatively small amount of code, you can actually accomplish a lot just with all these features built in. So this is just to give an idea of what you can do. And that's about it there. So why don't we take a look at, oh yeah, there's some useful methods here. Maybe I'll just quickly touch on. You can find the corresponding image pixel given a coordinate and the window. Some of this is stuff that you would have to kind of write by hand if you were to use just OpenGL on your own to display the stuff in 3D. So it's nice to have all these functions just kind of already available, already written for you. So let's see what this looks like. All right. So like I mentioned, so here's our point cloud in 3D, and the color of each point has been mapped to the near infrared channel. And then, as I mentioned before, I'm displaying the near infrared image at the top of the screen. And I've configured that mouse position handler so that if I mouse over this image, the corresponding pixel in the point cloud is highlighted, and we can see not just its position in meters here, but also its value in the near IR. So very interesting. You can for instance, you can see how the value increases in the near IR channel when you're mousing over these paint markings. So this is just kind of, a script that I put together in, probably 15 minutes, and it makes for actually kind of a useful point cloud analysis tool with comparatively little effort. So a pretty easy way to get started visualizing all of these images, not just in 2D, but in 3D as well, and both at the same time. All right. Let's go back to our editor and our examples. One of the really great things about the OSF format, or open sensor format, is that not only does it support, it's kind of a format that's kind of very conducive to Ouster lidar data because it supports these 2D images kind of in whatever configuration. You can add your own data to it, and that is useful if you want to do some image analysis, some processing, whatever, and then you want to save that and either share it with customers, colleagues, upload it to Ouster Studio, and so on and so forth. It's actually quite useful in that manner. And so I'm going to give a basic example of how that can be done, and then I'm going to show a kind of a more real world example that's a little bit more cool that really kind of highlights the possibilities. So in this example, as before, I am using the open source method to open that source file. It's got an iterable object of scans. But what I'm also going to do here is I'm going to, on this line, I'm going to instantiate an OSF writer object. Now that writer really accepts a file path It accepts a list of sensor metadata, and or just a single sensor metadata if you're just using a single sensor. And then as we iterate through the scans in the source that we opened, I'm going to take each of those scans and I'm going to add my own field to it. I'm going to add a field type of a floating point field type. It can be other types. These are all NumPy arrays. So, if you want to use integer types, you can use integer types. You can use different, 16-bit, 32-bit, whatever integers you want. You can use floating point. And then I'm going to just kind of make up some data. This data is what I've got here is I'm just interpolating the number of rows from 0 to 1, and I'm saving that for every and repeating it for every column in the image. And then I'm going to save that to the file. And I'm only going to do this for one scan, so I added this break statement here. We don't need to do this for every scan, but what I'm going to do is I'm going to then open up that example, and we'll just print out what that looks like. Oops. Okay, so this is not very, this is kind of as we expect. We see some values going from 0 to 1 here in this two-dimensional array. It's kind of abbreviated because that's kind of the default way that NumPy arrays get printed out. Very cool. So the data's in there. We know the data's in there, but maybe we want to actually visualize it, and that's where the next example comes in. What I'm going to do here, this is just a much more basic point viz example. I'm really just creating a single point cloud object. I'm using the field that I saved to that file as the color for that point cloud object here using set key. And then I'm adding that cloud to a point viz instance and running it. So really, really simple. This is, with only 12 lines of code, we're already visualizing our custom data. And there it is. So we have this nice colorful point cloud here, just with our own, where we're displaying the range data, the points that have been transformed into 3D, but then the color of those points is mapped to our custom data. All right, and I see that I'm probably running a little bit short of time, so I want to move right on to kind of the possibilities, where the possibilities of this custom data in OSF can really, really be useful. Now, obviously, a common use case for lidar data and kind of this sensor data in general is you want to be able to build autonomous vehicles, robots, so on and so forth that have some perception capability. So I'm going to run this example where we're going to use Ouster lidar data as the source to a YOLO perception model, and then we're going to identify the different vehicles in the scene and add the instance IDs of those vehicles to custom fields so that we can see them in 2D and in 3D. And this is just an open source perception model released under GPL3. So any of you can try this if you want. So what I'm doing is I'm switching the mode in the Ouster CLI visualizer here so that we can see the instance ID kind of mapped to a random color here for all the vehicles detected in the scene. And you can see these, I'm going to increase the point size a little bit so it's easier to see. You can see each vehicle distinctly identified with its own color. And what you can do with OSF is you can actually save this data to an OSF file using that OSF writer, and you can share this data with anybody who can read OSF. So if anybody's, if anybody else who installs Ouster SDK can use the CLI, and they can look at this data that you've shared with them with these custom fields in it. Let's just actually make this a little bit bigger, and you can even see some debug info that this script adds. Kind of shows the confidence and an instance ID of each vehicle that is detected using this YOLO perception model. So with relatively little code, you can really achieve a lot with the SDK, with the Python API. Okay. Oops. That is not the right screen. All right, what else do I have to show you? I think we've covered pretty much everything. So I think time check. Yeah, I think I'm kind of out of time, but we've covered a lot. We've talked about how to open up data sources, whether they be sensors or files, and iterate through the scans that are within them. We talked about the lidar scan abstraction, the lidar scan data type, and how it's essentially a collection of images. We talked about how those images, when they come off of the sensor, they're in a staggered form, but then you can use a single method called destagger to make them a little bit easier to see in 2 dimensions. We also talked about how to take that range data from those scans and visualize it in 3D using the XYZ LUT. We've taken a peek at some of the ways that you can customize point viz by using images, 2D images, 3D point clouds, event handlers, and so on and so forth. And we've also talked a little bit about how you could use custom fields to share the kind of the output of your analysis and share it with your customers and your colleagues. But we've barely scratched the surface. There's so much more in here. Lots of stuff we didn't cover today, including SLAM. So if you'd like to learn more, I would encourage you to check out the documentation page or visit the community forum, where there's a bunch of examples, including that YOLO example is available on the community forum. The links are down below. And also, this project is 100% open source using or under the BSD3 or 3-clause license. So, go to our GitHub, clone the repo, check out the examples there. You can use any of this code in your commercial product. And so, to get started, I would say go to our GitHub and check out the examples there. And it really kind of showcases some of the possibilities. And the link for the GitHub projects and the examples are below as well. Thanks for listening.
Awesome. Thank you so much, Tom and Michael. Great presentations, a lot of really valuable information. Appreciate all the work you guys did getting this set up. Was really, really fantastic. Here's what we covered today. Tom did a really good job of wrapping that up and summarizing that. So there is just one more thing that I wanted to touch on, which is we have officially released as of yesterday, Ouster Studio Web, which is our cloud-based platform. For those who are familiar with Ouster Studio Desktop, who have been using it to visualize, manage their data, do analysis and things like this, this is now the cloud-based version of this. We're super excited to release that to everybody. It makes it really easy to share your data with other colleagues or even your clients, and they can easily visualize it without having to set up any of the SDK or use Ouster CLI or anything like that. So we're super excited about that, and huge thanks to the team that's behind this for getting this all ready and released yesterday. Okay, let's jump into some Q&A.